afternoon, students. In the last class, we discussed the nuclear reaction, that is nuclear fission, right? So, along with the nuclear reactor, right? So, what is nuclear fission means? The splitting of the heavier nucleus into its fragments, that is of the lighter nuclei, along with it releasing the neutrons plus energy, right? So this energy we going to calculate if we consider the mass number is 240 of any heavy nucleus, right? So then the specific binding energy of the heavy nucleus of 240 is around 7.6 mega electron volt, right? So this one is the specific binding energy of the heavy nucleus. So this is we observed from the graph, that is EBN to that of the mass number 8, right? So here we getting the graph like this. So for maximum we are getting at A is equals to 56, that is equals to 8.75 mega electron volt. That is for mass number 56 we are getting 8.75. So almost from here to here we have a constant value, that is around 8 mega electron volt. So after that it decreases, that is less than 8 mega electron volt. So this mass number lies after this 170, right? So here the mass number above 170, the specific binding energy is almost 7.5 to 7.6 mega electron volt, right? So this nucleus is split into two separate nuclei of comparable masses. For approximate, we taken this one as 120 mass number, and here also mass number 120, right? So if these masses are having the same mass number 120, then it lies in the region of 30 and 170. Then specific binding energy of two nucleus of mass number 120 is having the value 8.5 mega electron volt, right? So here if you observe, the specific binding energy of the nucleus is 7.6 and specific binding energy per nucleon having the value of the individual nucleus is 8.5 mega electron volt. Then gain in specific binding energy, right? So gain is nothing but the difference of these two energies, 8.5 minus 7.6, then we get 0.9 mega electron volt, right? So from this we are going to finding the energy which is released during the nuclear fission process, right? So for that the binding energy relation we have EBN is equals to EB divided by A, right? So from this we are going to finding the energy. That energy we call as disintegration energy, right? So from this EB is equals to EBN into A, right? So here the gain in EBN is how much? That is 0.9 into mass number A of the heavy nucleus is how much? That is 240, right? So here we obtaining approximately 214 mega electron volt. That one we call as Q value or disintegration energy, that is Q is equals to 214 mega electron volt, right? So during fission process the energy released is around approximately equals to 200 mega electron volt. When the nucleus is split into its constituent nucleus, so then the energy released is around 200 mega electron volt, right? So this much of the energy which is released in the nuclear reactor during the nucleus is split into two separate nuclei of comparable masses, right? So this energy is utilized for kinetic energy of fragments and neutron. Right? So this energy which is released during this process, so that energy is utilized for the kinetic energy of the masses, that is comparable masses, along with the kinetic energy of the neutron. Right? So here the kinetic energy, as discussed in the last class, that is the kinetic energy of the neutron is almost around 2 mega electron volt. Right? So when these comparable masses, that is fragments of the heavy nucleus, while traveling having the kinetic energy, then these values, that is heavy kinetic energy associated with the surrounding, then this kinetic energy is converted into heat energy. So from this heat energy we are using to produce the electricity. So this is how the energy which is released during the nuclear fission process, right? So here considering one comparable mass of the mass number 240, so it is divided into comparable masses of 120 and 120. The specific binding energy of the heavier nucleus is 7.6 mega electron volt. So that is from the graph. Then the specific binding energy of the fragments nucleuses having the specific binding energy 8.5 mega electron volt, then gain in the kinetic energy, that is gain in the specific binding energy is 0.9 mega electron volt. Right? So from this we are going to calculate the value of Q, that is disintegration energy. So this energy is utilized for the kinetic energy of the fragment particles and also with the neutron, right? So as these are moving with the highest kinetic energy, then these particles interact with that means these nucleus interact with the surrounding, then heat is produced. That means conversion of kinetic energy into heat energy. So by utilizing this heat energy, so we are producing the electricity. Right? So this is about the nuclear fusion, that is energy which is released during the nuclear fusion. Right? So on the last process is nuclear fusion. So what is nuclear fusion? That is two or more lighter nuclei combined together to form a heavier nucleus. So the energy is released in the process. That process we call as nuclear fusion. Right? So what is nuclear fusion? So nuclear fusion is combining of two lighter nuclei. Right? So two lighter nuclei. This one is one lighter nuclei, and nucleus. This one is another lighter nucleus. So combined to form heavier nucleus. So along with this, energy is released. Right? So this process we call as nuclear fusion, that is fusing of two or more lighter nuclei to form the heavier nucleus, and the energy is released. So that process we call as nuclear fusion. Right? So what is nuclear fusion? The combine or the fusing of two or more lighter nuclei or lighter nucleus to form heavier nucleus. So this process we call as nuclear fusion, right? So there is difference in fusion and fusion. Fusion nothing but combining of two lighter nucleus, right? So for this we have example, that is two protons, that is protons is 1h1 and 1h2, 1, right? So when two protons are fusing, we are getting 1 H 2 plus one positron along with a neutron, so plus energy. So this energy is 0.54 mega electron volt, right? So this is one example. So here two protons are combining, that means two protons are fusing together to form one deuteron, right? So this is also the isotope of the hydrogen. Along with that, one positron is releasing and one neutron is releasing, and it releases the energy of how much? That is 0.54 mega electron volt. That means one fusion, this is for one fusion. That means one proton fuses with one proton, then we getting the energy, that is how much? 0.54 mega electron volt, right? So in the previous, that is in fission, the splitting of uranium into it constituents particles, or sorry, constituent nucleus. So along with this, energy is released. So this energy is how much? As we calculated, that is 200 mega electron volt, right? So if we compare the energy in fusion to the fusion, so in fusion the energy released is 200 mega electron volt when one nucleus is splits into two nucleus, right? So this energy is more compared to that of this energy, right? So this is only 0.5 mega electron volt. So in fusion, in fusion the energy release is around 200 mega electron volt, right? So this is one example, right? So if we take one more example, it is 1h1 plus 1h1. So here, so this one 1h2 along with 1h2. So here we are getting 2He3 plus 1 neutron plus energy. So here the energy released is 3.27 mega electron volt. So here for one fusion process, the energy which is released is very less compared to that of the energy released in the fusion process, right? So these are the two examples. So this one is the definition. So along this definition we have example, right? So here energy released per fusion process is very less. So this fusion takes place only at higher temperature. So this fusion process, that means if two lighter nucleus has to combine together, means it requires what? Higher temperature. So this temperature is of the order 10 to the power of 9 Kelvin, right? So for that purpose, nuclear fusion is also called as thermonuclear fusion. So this fusion of two nucleus has to combine to form the heavier nucleus, then it requires higher temperature, right? So if we need to combine these two nucleus, means it requires higher temperature, so it is of the order 10 to the power of 9 Kelvin, right? So that means 1 billion Kelvin, right? So that's why the nuclear fusion is also called as thermonuclear fusion. So thermo is nothing but heat, right? So that's why we call the nuclear fusion is also called as thermonuclear fusion, right? So why we need higher temperature to combine these two lighter nuclei, right? So as the atom, as already says, so atom is consists of the nucleus. So along with the electron is revolving around the nucleus, right? So when we applied higher temperature to these nucleus. So if we apply the temperature around 10 to the power of 9 Kelvin to this nucleus, then this electron which is revolving around the nucleus is spreads, that means splits out of this nucleus. So first reason is we need to remove this electron which is revolving around the nucleus. So for that reason we are applying the higher temperature, right? So this electron is splits out from the nucleus, right? So similar way here also one more nucleus, and here also we have one electron. From here also the electron which is splits out. So only the remaining is two nucleuses. That means here we take an example of one H1 and here also one H1, right? So at this temperature, these two nucleuses are positively charged, right? So from electrostatic Coulomb's law, so like charges are always repel, right? So like charges are always repulsed to each other, right? To overcome this one, that means here the nucleus is positive charge and here also the nucleus is positively charged. So according to Coulomb's electrostatic, these two positive charges are repulsed with each other, right? So during normal temperature. So when we apply this much of temperature, so this nucleus gains the kinetic energy and it overcomes this repulsive force, right? So for that purpose we are applying this much of the temperature, right? So understand this one, why we are applying high temperature to combine these two lighter nucleuses means, so the first purpose is the electron which is revolving around the nucleus has to split out from the nucleus and it is overcome to the repulsive force of the Coulomb's electrostatic force. So for that two reasons we are applying this much of the temperature, right? So for that reason we are applying higher temperature. So for applying this higher temperature, so nuclear fusion we call as thermonuclear fusion, right? So this one fusion is not takes place in the laboratories, right? So as fusion process we conducted that one in the nuclear reactors, but this fusion process will not takes place in the laboratories because we cannot provide this much of the temperature in the laboratories, right? So we are not able to generate this much of the temperature, and also this fusion process is uncontrolled. So we are not able to control the fusion reaction. So for that reasons the nuclear fusion reaction will not able to take place in the laboratories. The main reason is two, that is we can't able to supply this much of the temperature, that is of the order 10 to the power of 9 Kelvin. And the second one is it is uncontrolled reaction, uncontrolled chain reaction. That means we are not able to control this fusion reaction. So for that purpose this fusion reaction will not take place in laboratories, right? So this is about the fusion. So generally fusion takes place in the core of the sun or in the stars, right? So nuclear fusion generally takes place in the sun or in stars, that is sun and stars both are same, right? So in sun the fusionable material is hydrogen, that means the proton is the fusionable material, that means the fuel in the sun is the hydrogen. When two hydrogen combines together it releases the energies. So in sun it takes place proton cycle. So this one has number of reactions that takes place in the sun, that means the nuclear fusion that takes place in sun, so that cycle we call as proton cycle, right? So starts from first equation, when two protons that is hydrogen, having mass number is 1, then those are called as protons. Then these two protons are combined, that is fuses to form 1H2, that is deuteron. This is also the isotope of the hydrogen, right? So along with this one positron, right, positive charge of the having the mass number of the electron, along with this one neutron, nu, plus here the energy released is, so plus energy is released, so that energy is 0.54 mega electron volt, right? So again this proton E plus bombarded with the electron, so which are escapes out from these nucleuses, right? So then here gamma radiations are emitted, so plus along with this energy is released, so that energy is around 1.02 mega electron volt, right? So here we obtain the deuteron. So this deuteron, in Sun we have number of the hydrogen nucleuses. So this deuteron combines with the hydrogen nucleus, that is 1H2 plus 1H1, right? So we are obtaining the isotope of the helium, that is 2He3, right? So 1H2 plus 1H1. So deuteron combines with the hydrogen. So we getting the helium nucleus, that is helium isotope 2He4 plus one neutron is released. So along with the gamma radiation. So not neutron, it is gamma radiation. Plus gamma radiation plus energy. So here the energy release is about 5.49 mega electron volt. So again this helium undergoes binding with, that is fusing with another helium isotope. So we getting 2He4 plus 1H1 plus 1H1 plus energy is released. So here the energy is released is 12.86 mega electron, right? So this number of reactions, right? So we are calling this one as 1, 2, 3, and this one is 4, right? So this cycle we call as proton-proton cycle. Now if you observe here, in the nucleus of the, that is in the core of the sun, we have many number of the hydrogen nucleus, that is proton. We have several number of the proton. When two protons combine together, we get the deuteron, right? So this deuteron again combines with the proton, so we getting one helium nucleus, right? So this helium nucleus again it combined with this helium nucleus means, so these three cycles has to repeat twice, right? So here we have only one helium nucleus, so for bombarding of this helium nucleus with another helium nucleus means these three reactions has to take twice, right? Twice nothing but if we multiply, so this whole equation by 2 into 2 and into 2. So then only we get in this fourth equation, right? So if we rearrange and write these above three equations, so we can write. So first one becomes 2 1H1 plus 2 1H1. It gives rise to 2 times of 1H2 plus 2 positron plus 2 neutrino, and here the energy is released 0.54 into 2. So here we getting 1.08 mega electron volt. Right. So the next, the second one is 2 positron plus 2 electron. We getting 2 gamma rays plus 2 gamma rays plus the energy is 1.02 multiplied by 2. So here we getting 2.04 mega electron volt. Right. So next, the third equation is multiplied by 2. That is 2 times of 1h 2 plus 2 times of 1h1. So here we getting 2 helium isotope, 2 into 2he3 plus 2 gamma plus energy. So 5.49 into 2, that is 2 9s are 18, right? 2 5s are 10, that is 10.9. Right? Now we need to add these energies 1.08, 2.04, 10.98 and 12.86. So if we combine all these 4 reactions together, that means this one is the 4th reaction along with this 3 reactions, right? Either we can write like this or we can directly write this form along with the 4th equation, right? So this gives what? The proton-proton cycle. So this is for understanding purpose, I will explain here, right? So as one proton bombard with the another proton, we get one deuteron. So this deuteron again collides with the proton. We are getting one helium isotope. So this helium isotope has to bombard again with the same helium isotope, but here we don't have any another helium isotope in this reaction. So for that purpose, we need one more helium isotope. For that reason, we need these 3 reactions has to appear twice. So appear twice means all these 3 reactions has to multiply by 2 times, right? So then we get these reactions. Then here, if you observe here, 2 helium isotopes are there, right? So these here 1 and here 1, right? So then these 2 helium isotopes combine or fuse to form one helium nucleus. So this is the helium isotope and this one is the helium nucleus, that is stable nucleus, that is 2He4. So if we write this one in general form in one equation, we get this one, and here is second equation, here is the third one, and in the last we have the 4th equation, right? So if we write in general, that is 4 1h1 plus 2 electron, so we getting 2He4 plus 2 neuron plus 2 gamma radiation plus energy. So here the total energy is 12.86 plus 1 plus 2.04 plus 10. So that much energy is around 26.78 mega electron volt. So this one is the final energy which is released during the fusion process, that is in the sun. So it has series of cycles. So here we have 4 cycles. So that cycle we call as proton-proton cycle. Right? So this is about the nuclear fusion. So nuclear fusion general example is, if we write the first equation, then only we can write. So these all can be written as the nuclear fusion reaction. So in sun we need to write all the 4 equations, then only it completes the proton-proton cycle. Right? So this is about the nuclear fusion. right? So on the last is the differences between nuclear fission and nuclear fusion. Here nuclear fission and here nuclear fusion, right? So if we make two columns, so the first point is the definition of singular, nuclei is plural, right? So nuclear fusion and nuclear fission. The first point is definition of the fission and definition of the fusion. So the second point is it takes place in it takes place at ordinary temperature. So it takes place at ordinary temperature. So here the opposite for that one is it takes place under high temperature of order 10 to the power of 9 Kelvin. So that one is the second point. So next, the third point is it can be controlled. So here in fusion, it cannot be controlled. So it cannot be controlled. So next, so energy released per fission. So energy released per fission is more. As already explained, so per fission, the energy which is released is around 200 mega electron volt, right? So here the energy released per fusion is less. So next, energy released per neutron. So energy released per nucleon is less. So don't confuse with the process. This is one process. When one nucleus splits into its constituent nucleuses, then the energy released is more. So here the energy released per nucleon. So for one nucleon, that is for one proton or one neutron, so that energy is very less, right? So here the energy released per nucleon is more or high. And the last point is the end products. So in fusion process, the end products are radioactive. So again it undergoes decays and again it releases the energy for stabilizing the nucleus, right? So the end products are radioactive. So here the end products are non-radioactive. So the last point is It is the principle for atom bomb. So this is the principle which we are using in the atom bomb, and here it is the principle of hydrogen bomb. Right? So in case if they ask for 3 marks or for 5 marks, if they ask for 3 marks, we need to write any of the 3 points. So if they ask for 5, so we need to write any of the 5 points. Right? So this is the difference between nuclear fission and nuclear fusion. So here approximately we have 7 points. So if we need to add means we can write one example, that is one reaction for both nuclear and that is fusion and fusion, right? So these are the points. So these points are already explained in the theory. So this one is the definition. So it takes place under ordinary temperature. So it takes place at the higher temperature of order 10 to the power of 9 Kelvin, right? So for that reason only the fusion process is cannot be controlled. That means it is uncontrolled nuclear reaction. So fusion process is controlled nuclear reaction. So here energy release for fusion is more, that is approximately 200 mega electron volt is released here. So here the energy release for fusion process is almost around 1 or 2 mega electron volt, right? So energy release per nucleon, that is for per proton or neutron, that is energy release is less. So here the energy released per nucleon is more, right? So here the end products are radioactive, right? So the heavier nucleus which splits into constituent nucleuses, then those nucleuses are radioactive in nature. Then again it undergoes decay. So for the stable of the nucleus, right? So here the end products are non-radioactive, and it is the principle which we are using in the atom bomb, and so the fusion process, that principle we are using in hydrogen bomb, right? So these are the points of nuclear fission and nuclear fusion, right? So by this we completed the chapter. So from this chapter we having 6 marks, right? So the possibility of questions which are coming is for 1 marks, compulsory one question will be in 1 marks, and 1 marks, that is for 5 marks, one question will be compulsory. So maximum possibility of coming is problem from this chapter. So that is also from the radioactive and also binding energy. Only on these two concepts we are getting the problem, that is for 5 marks. So these problems are very simple by using 3. Here in the radioactive we have 3 relations, and in binding energy we have only 2 relations. That is, one is mass defect and binding energy and specific binding energy. So from this chapter we have maximum 6 formulas. So 3 in radioactive and 3 in binding energy, that is EB, EBN and mass defect delta N. Right? So here in radioactive that is half life and mean life. So along with that activity R is equals to lambda N. Right? So 1, 2, 3 formulas, and here also EB, EBN and delta N. So if we know all these 6 formulas, then we can easily simplify the problems, right? So by this we completed the chapter nuclei. So in the next class we will start with the new chapter, that is semiconductors, right? Thank you. Doubts?